if you are here, you may take this road, or you may stay at this park, these parks, for several hours. Then, if tsunami hit and no wall operates, no wall funked, you are safe because that location is somehow higher than the other place. So that simulation, I use the digital elevation model. So the higher place shows higher. There is no tsunami at all. So you can take this road, or you can use this park. Not here. For your suggestion, Port Island, the southern part of Port Island is safer. It is higher altitude than northern part. Therefore, stay here is better. If earthquake hits today, tonight, or tomorrow, you may stay here, then safe. Maybe upper stairs, more safe. But if you stay around here occasionally, if you take port liner, it's okay. But if you at the ground level and stay here occasionally, you may come to the south. Okay. I would like to change. So this is the other one for simulation. So at the harbor land, the tsunami height is as higher than the people's height. Therefore, you don't have enough way to evacuate. So this is the people's height, and this is tsunami height. And there are cars, so they hit and exploded like that. This is the photo taken after the typhoon high tide hit a park at Rock Island. So very small amount of water intrude into the park, but that water is enough to push the cars, and they hit each other because water collect to the lower place. Then the cars collect at the lower place, then they explode. So this may happen after tsunami. So you don't know when a disaster happens, but the simulation suggests you what will happen when a disaster happens. So I think it is the reason why we need to simulate a disaster. But for simulation, we need to put the data of cities into input file. So that is the question of the first half. Disaster simulation needs programs and data, both. So real city should be changed the form to cyber city. We just place this arrow, but the arrow requires a lot of work. as you did with the with help of the generative AI. Then the model input data for numerical simulation you can use. And physics and physics-based mathematical equation. Then many people work for programming for numerical simulation of the physics. So both of them are necessary for HPC. And that HPC can simulate the situation. Then we can use the results for analysis, visualization, and so on. So I want to say that this alone is very difficult. So in our team, in RIKEN, we built this data processing platform for translate the city data into numerical simulation. City data is not uniform. We have commercial resources like Google. We have official databases I would like to show later. We have monitoring data, sensor data, and so on. So we need to translate for earthquake simulation, tsunami simulation, and so on. Or Professor Larry's simulation requires his commercial data for numerical simulation. Okay. So in Japan, we have many many databases like Plato. So this is made by Japanese Ministry of Land Infrastructure, Transport and Tourism. Built that three-dimensional building data. It is Tokyo Station. So if you put the texture, it looks very attractive. But the most important specification of that data is not the texture, but the data itself. If you point out one building, you can see how tall, how many stairs in under the ground, and areas and so on. The structures and so on. So not only this building, but this relatively smaller building also has this kind of data, because for tax management, all building has their own registration, and it has height, area, volume, made by steels and concrete and so on, to counting the tax. From the previous, tax is one of the most good reason for identifying the the buildings is. Therefore, these information should be translated into the numerical simulation. Okay. Then from public data to simulation, I would like to come back here. I came back here. So for this is a bridge pier, bridge foot. And so for making it, we have this kind of design draw that is written in vector like PDF. And so if you read that vector, if you make a program to read that data, we can build this kind of input data for numerical simulation easier. So that is the reason why I gave a problem for you to read this kind. And now recently, as some of you get correct answer, you can use the generative AI for making this kind of program. So this is a summary of that problem as well. If you use the Gemini, it makes the program, but the answer is not correct, I guess. Yeah, I tested, not I guess, but I tested, but the Gemini still have wrong answer. Chat GPT 5.2 plus Python, it works well, but Chat GPT 5.2 plus C++, it doesn't work well. I'm not sure the reason why. If you want to use C++, you need to install lots of libraries. That is troublesome, especially for supercomputer. So our system can install libraries within the virtual environment without any troubles. So our system is somehow good. So to make such kind of building model, you prepare map, you prepare building data, you prepare address table, and for making a building model. So in Japan, we have several coordinate system for locating, pointing the positioning, not longitude and latitude, but our own coordinate system as well. Therefore, we have to change the coordinate, but it is somehow just an arithmetic problem. It is a coordinate problem, so you need to connect with the world coordinate with address, this port island address and so on, and you need to refer the local coordinate versus building specification and local coordinate and position from the reference point in PDF. You have to do that. Then you connect them to get this kind of building model. This is here, Fugaku. This building is built 2010, May 31st. It has 6 floors and height is 24 meters. And it built by steel and so on. So this kind of information, we can connect the public data and private data. Then we built this kind of building model for entire Kobe city that has 400,000 buildings inside. Then we shake that building with Nankai earthquake estimated, or Hanshin earthquake waves. Then the building, some of buildings collapse in the numerical simulation. Some of buildings still alive after the simulation. We also, that part is in the cloud using SaaS system, software as a service system. So we put the key, we install the job with API key to SaaS, then SaaS can get triggered, and simulation of ground motion, simulation for the structures can be calculated. Then the result will be appeared in the cloud. So people do not need to have their own environments, but they just use web browser for triggering the numerical simulation. So up to here is is for the preparing the data for numerical simulation. If you have any question up to here, I would like to accept your question. No? Okay. Hi.
I'd like to ask, thank you, Professor. I'd like to ask, where did you get the data? I mean, you have the like the very good metadata of buildings, and where did you get it? Thank you.
I see. So we have many databases, but in terms of building, you can watch the plateau. T-E-A-U, plateau, Japan. Yeah, well, yeah. Then I'm sorry. I guess that you may have English plateau, project plateau, like that. Then that plateau has not only the viewer, this is viewer, but also the data download system as well. Maybe around here you may have some tags around here. Open data, yeah. So maybe you may have some tag, but open tag, open data. So G Space Information Center. And I'm sorry in Japanese. Yeah, there is English one. Yes. Our Geospatial Information Center connected with the plateau. Then you can download from here. Okay. Welcome. And Yeah, it's a Japanese. Okay, sorry. Please. Yes, we have. Ground motion and ground, in terms of the ground, we are using GSI, Geospatial Information Authority of Japan. Yeah, GSI. I mean, I guess you may Google GSI Japan is here. GSI, and there is borehole data inside it. But actually speaking, that borehole data is the cost. If you want to have a fine data, you have to purchase. So free data is closer, and you get the more detailed data available, because most of the time landowner is public, so they don't allow public to dig a hole. But if a company pay them to dig a hole or some other contract, they can get data and they sell. So if you are interested in, please ask someone like me. Please ask me as well. Yeah, I can give a good way to reach the final data if you need, but it costs. How much? Okay. Not much expensive. Yeah, like ChatGPT subscription. Almost. Yeah. So some month for a year or something. Not one, but whole. Yeah. But you cannot. You can just use. Yeah. Any other question? Okay. So if you want to ask question, please let me know. I will stop. Then we are moving to the numerical simulation. From this part, I borrow materials from Professor Ichimura, University of Tokyo, the University of Tokyo. He did this kind of work with Professor Fujita. He did this kind of work using K-computer and Fugaku. As you already know, most of you may already know, we have to use a partial differential equation for calculating the numerical simulation, calculating the geotechnical movements after the earthquake, during the earthquake. And that partial differential equation should discretize and to calculate by computers through linear equation. And then after the discretization, the formula becomes this shape: matrix, vector, and vector. So you just, for getting the calculation, you just need the inverse of this A matrix, then you can solve X. But the A matrix has extremely large, like 33 trillion units. It's huge amount, and normally it is not easy for you to calculate the inverse of A. Previous work by Earthquake Research Institute of the University of Tokyo, by using K, they have two cutting edge research in 2014 and 2015. During that, they built the first solver for large finite element method. Basically, they use a conjugate gradient. So they calculate the steepest slope for terminating the errors. So in outer loop, second ordered tetrahedron, I use solve the preconditioning matrix roughly to reduce the number of conjugate gradient loops. Use multi-grid method to reduce the cost of the preconditioner, and use single precision in preconditioner to reduce computation and communication. Then solve the fine loop. So second order tetrahedron. By using it, they use K computer, Oak Forest Parks, and Fugaku, Summit, and this one efficiently. Size up scalability is 96.6% efficiency from almost 10,000 cores to 660,000 cores. So it's a big scalability. This is side up scalability, and this is speed up scalability, is 76% efficiency from 9,000 to 294,000 cores. So almost the scaled. Then they can calculate from fault to city structure with one numerical code. FEM earthquake simulation guarantees accuracy down to 10 Hertz. Implicit time integration with 18 billion FEM point and 56 billion degree of freedom. So this is the calculated data after 15 seconds, 16 seconds, and 17 seconds. So the map shows the color shows the velocity norm. It is well calculated. Then afterwards, in 2022, parallel computing with data learning for large-scale earthquake simulation, they did. So this is the fundamental equation of the numerical simulation. This is norm matrix, change time by time. And this is norm vector. And this is unknown vector that is position change, delta U. U means position. So it has 100 billion degree of freedom. So to solve 10 to the 18, so 10 exaflop scale problem by using Fugaku that has 0.42 exaflops. So it requires 25 times of ability of Fugaku. Therefore, they develop a new method. During calculation, they have A1, F1 at one time, A2, F2 at second time, A3, F3 at third time, and so on. And each time they have X value, unknown matrix. So A1, A2, A3 change time by time. Most of the time differences are small. And so they use that A1, F1 for deep learning to get a better X. So developed an algorithm integration of HPC and data learning. That is equation-based approach and data-driven approach with high-performance computing on supercomputer. Hardware improved from K is 42% to Fugaku, and 10 exascale has been achieved. So they have 25 times efficiency, then they reach the 1,000 times scalability. That is groundbreaking solver. So this is the end of my talk. So you understand it. So for nowadays, you can use the deep learning method. And therefore, by learning the time by time, reducing the terminated time for calculation. I mean, the closer estimation can be achieved using the artificial intelligence. Then you can get higher accuracy within the smaller time. So that is what I want to say. So this is the end of my talk. I would like to accept your question if you have.